Hello, everyone. This is the last little recording for Chapter 3. It is a very short recording, I just wanted to add it on here at the end. And it is Chapter 3.6. It's how to do the inverse of a function. So far we looked at function operations where you had to add, subtract, multiply functions. We also looked at function composition, where you had to put one function inside of the other. So today is looking at inverses of functions. So first off, an inverse of a function notation. So for the notation of a function is f of x, the inverse, they do use a little -1 on the f, okay? And that is read f inverse. So kind of mathematically, I don't have to actually tell you to find the inverse. I could just write f inverse, and you would know that that's the inverse. What happens in an inverse function is basically the x and the y switch. And that's truly what you do. So basically the range becomes the domain, and the domain becomes the range. So if I was to give you a basic function, say, for example, 1, 2, 3, 4, 5, 6. So the inverse of that function then is going to be 2, 1, 4, 3, 4, 3, and 6, 1. Okay, and it gets a little technical. You get a little deep into inverses. Of course, this one is a function, and when I find the inverse, it is also a function. So you have to be careful there, because sometimes if you would switch that, it might actually not be a function anymore. But that's the idea. But both of those are functions. Notice the x does not repeat, so they both are functions. All right, so we're going to do 3 things today. We are going to find an inverse. We are going to prove that something's an inverse. And then we are just going to look at a basic graph of an inverse, just so you can kind of get a visual of what's happening. Okay, so first thing is finding an inverse. So how do I find an inverse? And it's very easy. So as far as finding an inverse, let's say f of x equals 2x minus 4. Okay, so the first thing you do is switch the x and the y. And literally switch the x and the y. Well, now you might say, wait, where's y? Well, if you recall last lesson, f of x is the exact same thing as y. So don't forget, this is y. So when you switch the x and the y, it becomes x equals 2y minus 4. Once you switch the x and the y, then step 2, you are solving for y. Okay? So now that I solve for y, I'm adding 4 to both sides, and that just becomes x plus 4 equals 2y. Divide by 2, and you end up with y equals x plus 4 over 2. That result is your inverse. Okay, so we call that f negative 1 of x, not f of x, because f of x is not there. You should be able to look at it. You should see opposite operations. Instead of times 2, you should see divide 2. Instead of minus 4, you should see add 4. But the steps are to switch x and y, solve for y. That result will be your inverse. Okay. I have 2 more here to get a little bit tricky, because they get a little tricky on the other side of things. But I at least want you to see the opposite operations happening here. Okay, so here's 2 functions. Let's find the inverse. So first off, that's a y. You need to literally switch the x and the y. Solve for y. Resolve. You get x minus 3 equals y squared. The opposite of a squared is the square root both sides. So the square root of x minus 3 is equal to y. That is your new inverse, and that is the inverse of that function. Basically the opposite of the given function. Same thing here, y. So you need to switch the x and the y. How do you get rid of a square root? Well, you square both sides, and you guys saw that in the other lesson. We just square both sides. Once you square it, it goes away. Subtract 1, you end up with x squared minus 1 equals y. That new y is your inverse. So basically, it's two steps, switch the x and the y and solve for y. So that is how you find the inverse, okay? And we'll graphically here in a second at this first one. But as far as finding that is how you find an inverse. Okay, now something else you can do. You can actually prove. And when you guys see this word, you might have a panic attack. I always hated proofs in high school. But this really isn't a typical proof. But prove that two functions are inverses of each other. And there is a formal kind of proof, I guess, to follow. All right, this is going to take us back to a couple classes ago. So how do I prove that two functions are actually inverses of each other? Well, you have to show that f of g is exactly the same as g of f, and in fact, those both equal x. Okay, notation-wise, I can do f of g equals g of f. Sorry, excuse me. Equals x. And does that look familiar? These here are your function compositions from last week. Okay, so these are your function compositions from last week, or from last video. I'm saying last week. I did the video yesterday, I'm saying last week. So these are the from the last video. Okay, so how do we do function composition? Well, that's the one where you had to put the one function into the other. So we are going to prove that two functions are inverses. And I give two examples here. So prove that f of x equals 3x minus 7 and g of x equals x plus 7 over 3 are inverses. Okay. So we have to first do f of g of x. And what that means is we start with function f, 3 blank minus 7. Remember to leave that blank because the second function g is going inside of that x. So x plus 7 over 3. When you simplify this, it usually works very beautiful. The 3's cross off, you're left with x plus 7 minus 7. Plus 7 minus 7 gives you x. Now that's not enough. You technically have to do g of f as well. Okay? So g of f means this time we're starting with g. So x plus 7 all over 3. And inside of that, this time is going the f function, which is 3x minus 7. Simplifying, there's nothing to distribute here, so we can just drop those parentheses. And when that happens, the 7's cross out, the 3's cross out, and you end up with x. Therefore, that is your proof. Since you got both x's for both of those, then in fact, these two functions are inverses. Funny story, calculus one year, I had a kid on a final exam say, oh man, please give me credit. I know they both have to equal x, but I don't remember what to do. So I had to give him a couple points. But this is the idea. So as far as proving they are inverses, you have to do the function composition. Okay, so I will be looking to see if you do that. You can't just start with one and find the other. This is an actual mathematical proof, so you do have to follow strict ways of doing proofs. Okay, let's do one more example of that. Just to make sure we have that same example too here. F of x equals the square root of x plus 2, and g of x is equal to x squared minus 2. Okay, and one could probably look at those and say, hey, they look opposite to me. One has a square root, one has a square, one has a plus 2, one has a minus 2. Obviously, they look like opposites. Can I just tell you? No, you have to do proof. So starting with function f, square root of x, which I'm going to call blank, plus 2. And remember, into that blank is going g, so x squared minus 2. Underneath that square root, you can drop those parentheses because there's nothing here to distribute except the 1. So once I drop the parentheses, the 2's go away. The square root of x squared does become just x. Likewise, the other way around, g of f. So if I do g of f, I start with function g, which is x squared minus 2. Remember, put that blank in there, and I use parentheses usually for that x, okay, when I write that. Okay, so f is going inside of that, so square root of x plus 2. you square root, goes away. You end up with x plus 2 minus 2, and you end up with x. So voila. In fact, those two are in fact inverses as well. Now, if they didn't end up both equaling x, then those would not be inverses of each other. Okay, and you would readily see that. So that's kind of the idea there. Okay, so as far as graphing, I kind of wanted to look at something here so you could actually see this. Okay, so I want you to graph f of x equals 2x minus 4. All right, and we're going to make a nice neat graph. So let's go back to what's called mx plus b. Or we could actually do an xy table for this. So as far as an xy table, if I plugged in -1, I end up with -6. If I plug in 0, I end up with -4. If I plug in 1, I end up with -2. And if I plug in 2, I end up with 0. What's it with 3? 3 ends up with 2. Okay, so you can do xy tables for these. And there's not much hassle for them. Okay, pretty easy math. So -1, -6, off my chart. 0, -4, 1, -2, 2, 0, 3, 2. Okay, and there's the line. Right, so that would be the line for that function. Okay. Now, as far as inverse, couple ways to do the inverse of this. The easiest way to graph inverses is literally to switch the xy table. This is the table for the original f of x. Okay? If I wanted to graph the inverse of this, then if you recall from the beginning of this video, you would literally just switch the x and the y values here. Okay? So let's go and graph those. -6, -1 is not my graph. -4, 0, that's going to be over here. -2 and 1 is here. 0, 2 is going to be there. And 2, 3, there. And this line is going that way. Well, not really a regular line. Let's draw a big one here. There's a block on here. That we can just imagine it like an arrow. Okay, so there's the graph of the inverse. Now, what you're going to see is a really cool property here. So this, oh, by the way, let's actually find the inverse. Ooh. Okay, so remember, how do I find it? I switch the x and the y, and I solve. So x plus 4 equals 2y, divided by 2. End up with x plus 4 divided by 2 equals y. And you can actually divide both of those by 2 equals y. So y is equal to 1/2 x plus 2. And that is your inverse, guys. Okay? F negative 1 of x. So what we just graphed up there, 1/2 x plus 2, so that should make sense. Start at 2 and 1 over 2. So it does. Okay, and that function should fit all of the answers for that as well. All right. Now the cool thing that happens here is this picture then is completely symmetrical. That's why I looked at the word there. Completely symmetrical about the line y equals x. If I draw the line, I'll draw it in red here. If I draw the line y equals x, that line will go right up through your graph. Okay? And it's kind of neat. It literally slices it in half. And why is that? Because the true meaning of an inverse is you switch the x and the y. So what happens is that it flips about that line. So the x is interchanged with the y, therefore it completes the opposite picture of it. So, but if you were to graph two functions, they would be perfectly symmetrical with that line every single time. Okay, so it's kind of neat. You can just see the symmetry happening there. So we're functions are complete opposites. And hopefully you can see over here at the chart, this would be the domain, this would be the range. It literally switches. So in the function, in the inverse down here, the domain literally becomes the range, and the range becomes the domain. So it is switched. So keep that in mind. It does switch for the functions. Both of these are still functions. Okay, so the x's don't repeat, so we're still good there. But that would be a typical, just a kind of a graph of inverses. Okay, so you could actually do that to look to see if two functions are actually indeed inverse of each other. But that is really it. The main thing you guys will have to be able to do, you have to be able to find an inverse, and you have to be able to prove that two functions are inverses. Okay? All right, with that said, that sums up chapter 3. So I hope you guys all have a good weekend, and I will see you soon for chapter 4.